yeah, I received a complaint that my abstract wasn't clear enough about what I'm going to cover. So this is maybe a bit more fundamental than covering any research. We're going to do the basics of program synthesis, and then we're going to maybe touch on a little bit of how you can combine machine learning and program synthesis. But you are the first people I've given this to, so you're the guinea pigs. So I'm not entirely sure how much we're going to cover. If this all goes well, then by the end of it, you will have all built a program synthesizer. Don't know how well that's going to go, though, so we'll see how far we get. Right, can I change slides? Yes, I can make the robot appear. Can I have the next slide? Yes, okay, so what's program synthesis? Who has done anything with program synthesis before? Guy, you're my PhD student, so that doesn't count. Okay, has anyone who isn't my PhD student done anything with program synthesis? No, okay, right. If you get stuck at the point where we're coding stuff, you want to go and talk to Guy or Ishuan or possibly Joe, although Joe is only just starting, so I would say that Guy and Ishuan are your main people to ask if you get stuck.
So could you define synthesis? How would you say?
Okay, so I'm going to say that synthesis is anything where you're automatically trying to generate code or expressions that satisfy some specification. So I'm going to be a bit more specific, and I'm going to say I want this to be techniques where the code is guaranteed to satisfy a specification. So I'm ruling out in that category best guess techniques. There are a number of ways that we can give specifications, and we're going to go through some of the standard ways in synthesis that we can do that. I'm going to talk to you a little bit about some applications to try and motivate you as to why you should care about this. So even if you think you've never done anything with synthesis in your research, you have potentially used it. So if you use Excel, it's got a thing in it called FlashFill and now FlashFill++, where you start typing some things in a column. You're like, oh, you put sort of a name and a surname in one column, and then you want the other column to be just the first initial and the surname. So Excel can autocomplete the formula you need to do that with, and it's using program synthesis to do that. There's a paper at the bottom, which is a citation for that. You could use it for deobfuscation. So there's a bunch of work where if you've got a bit of code that is really big and weird, you can use program synthesis to try and come up with an expression that is slightly less big and weird, which might be useful if you want to, say, reverse engineer something. Might be useful if you just don't want big obfuscated blocks of code in your code. You can use it for stuff like, so similar vein, you can use it for translating code from a low-level language to a high-level language. So you might have a bunch of machine learning code in C, and that's not as fast as it could be. So you can use program synthesis to translate it into a high-level DSL like Taco, which lets you then compile it super fast using the Taco compiler, and then you've got fast code. So you can use it for this sort of program lifting. Or also to PyTorch or NumPy. You can use it to help machine learning plan. So there's a couple of cool papers where, so if you've got sort of sparse rewards, you can use machine learning to try and explore those sparse rewards. But if you combine it with program synthesis, the program synthesis can help you come up with like sequences of actions that you need to do in order to achieve some goal, and then the machine learning is much better at achieving that goal. You can use it to learn from sparse data in science. This paper is doing some biology stuff that I don't really understand, but I recently had some undergraduate students who were using program synthesis to learn from data in sport. So I had one student who was using program synthesis to learn from GPS data in football games to try to detect what combinations of like GPS data mean that certain football events are happening. So you're learning predicates that can tell you when a corner is happening or when a goal is being scored. That's harder than you think because the ball doesn't have GPS data, only the players have GPS data. Yeah, so there are lots of things you might do with it. There are maybe things you might do with it in your research. I don't know what your research is, but I'm always out hunting for nails for my big hammer, so maybe you have one of the nails that my hammer could hit. But there are a couple of important questions if you want to use synthesis, and we are going to try to answer those. So, I said that you want to be generating code that satisfies the user's desires, the user's specification. The first question is, how do we capture the user's intent? Because the obvious way of capturing, you want a program, the obvious way of describing precisely what that program should do is for you to just write the program, and that obviously defeats the point. And then once you've captured the intent, the next question is, well, how on earth do we find a program that matches that intent? So, in these couple of hours, we are going to go through ways of defining the user intent, some common algorithms for searching the space of programs to try and find something that satisfies the intent. I'm going to talk about CGIS, Counterexample Guided Inductive Synthesis, which is the classic synthesis algorithm that everyone will mention as soon as you go beyond sort of giving your specification as examples. And we're going to briefly talk about machine learning if we have time. We are also going to implement some stuff, potentially. There was a GitHub link for downloading a GitHub repo. How many people have not done that? How many people who have not done that would like to do that? Okay, then I will skip all the way back to... Okay, that's the link at the top. It's not a big repo, it should download fairly quickly. I'm also not pretending that my code is beautiful in any way. I wrote this in Python because I assume that everybody is at least a little bit familiar with Python. It's not pretty, it's designed just to be a repo that you can play around in. Actually just write that up here, couldn't I? I've got a pen. Or maybe I can't because I've been defeated by getting the lid off the pen. What?
If you're strong.
There are other pens.
That one was easy. Thank you. Cool. Right. Okay. So, I'm going to talk about ways of defining user intent. Maybe just to see if anyone is awake before we do that. Any suggestions? If you want it, what would your ideal program synthesizer input be? I've got a magic tool, it will write code for you. How do you want to tell it what code you want? But what's the specification? Okay. You want the logical specification. So is that like formula? Pre-post conditions. Okay.
A user prompt on ChatGPT.
A user prompt on ChatGPT, so natural language.
Yeah.
Tests examples. Yeah.
A simple program that I know is right, but maybe not efficient, that I want to make.
Okay. Inefficient program, but like a reference program.
ECG brainwaves.
ECG brainwaves. I'm not sure we're there yet. Okay. Cool. Apart from the MRI option, any other thoughts? Sorry? Oh yeah, okay, so some kind of data. So I guess that's probably similar to input examples, but maybe you have more of them. Yeah, I guess you could collect other data from programs. I guess you could have like traces through the program. I guess you could have like sets of similar programs. Okay, cool. I'm going to go through all of the ways that I think there are synthesizers out there that you can use, one by one. This Venn diagram took me ages to come up with, so I really hope no one's going to query it as being inaccurate. But I think I'm starting with PBE, which I was surprised was not the first thing anyone suggested. So PBE stands for Programming by Example, and it basically means that you give some inputs and some outputs. So it's pretty straightforward. What does this program what program satisfies this? Addition. It adds two numbers. Yeah. So you just give some inputs and some outputs. What are the obvious disadvantages with this? Yeah, you've only got a few examples. You're basically under-specifying it, right? Like you could, maybe I wanted addition, but only if the numbers are positive, and I wanted something else if they're negative. Like you're under-specifying the program. But one of the advantages is that PBE's specifications are really easy to write. Yes, so that's what that one does. Let's do this. Give me a set of examples for Max. This one is a little bit more, it's not quite as obvious as addition, so yeah. Give me some. Give me one example. Yeah, the input.
Yeah, the same. 2, 2.
Okay, 2, 2, and it returns 2.
Yeah.
Cool. Anything else? That's not gonna specify my program for me. Give me an example.
Infinity of -3.
You're a terrible specification writer. Infinity of -3, and it's going to return infinity, maybe. We don't have a maybe option here. Okay, I still don't think that's going to give me, okay, anything else? Okay, kind of my point is that we're not going to get a complete set, like it's quite hard to come up with a complete set of input-output examples because we're always under-specifying this. And with something, so even if we ignore the real edge cases, like when we start having like overflow or when we start having sort of infinity in our type system, even if you ignore the real edge cases, you still have to think quite hard to produce the input-output examples to cover all of the cases if you have a program that has any kind of control flow in, and it isn't just one if and else can be enough that you have to think about it a bit. Yeah, so one of the big issues here is that we're under-specifying the problem. Can we do better? If you've tried PBE and PBE isn't working for specifying your programs, the next step up is usually to look at first-order logic specifications. So there's a whole world of synthesizers that work on simple first-order logic specs. And what that means is we are looking for, does there exist a function P such that for all inputs X, some first-order logic formula holds, and that formula is sigma? Looks like a question at the back.
I have a stupid idea with the previous option.
Yeah.
What if we use like a random sampler to get the samples and then use the SAT solver to ask if it's been made for the entire state space, which should be an easier query than finding the program itself. And if it found a counterexample, we keep adding it and do it in that way, and then you can have a by example thing that can get the edge cases directly.
So we have a random sampler which gives us example,
Actually,
gives us inputs.
We can even remove the random sampler. We go for a random program. We ask a SAT solver, does it meet the spec? If not, give me an example. We keep adding that example, and then we can.
What you are describing is CGIS, so just hold that thought for about 20 more slides.
Okay.
Yeah, what you're describing is counterexample guided inductive synthesis. We'll get there. But the thing with counterexample guided inductive synthesis is you have to decide what you're going to do to get to guess the programs. So we still need to get as far as having a search for examples before we can get to that bit. But yes, you've just invented something that is probably one of the fundamental contributions in synthesis. So well done. It is unfortunate that you are about 20 years too late, but if this was 20 years ago, I'd be like, it's amazing. Logical specs. Oh, yes.
Sorry, I might be doing pedantic, but you said it's first order logic specification. And
The
P ranges,
sigma, this is first
yeah,
order.
P ranges over function, so it's higher order. In that sense,
Yes, so when I say it's first order, I mean this specific bit here is first order.
So like
the
the
sigma
follow-up,
is quantifier free in first order.
okay.
Uh,
This is like the meta level thing that like you're saying there exists a function P. So
Yes.
that okay.
Yeah,
So
there
that's
exists a
not
function.
part of the logic.
Yes.
Yeah.
Depending on what your space of P is, this formula can be first order,
Okay,
but
yeah.
obviously if your P ranges over,
Yeah. It can be higher.
yes. But specifically, I require that your specification is. I mean, actually, I require that it's quantifier free, so more than
Okay.
first order.
Oh, okay.
I could have put the next bit up, and then I wouldn't have needed to say that. Yeah. Give me a spec for Max. I'm really into synthesizing programs that calculate the maximum of something. It turns out I just haven't discovered that there are libraries for this. So I'm going to need someone to give me a specification for this. Or I'm... Okay. F of x, y is greater than or equal to x, and it's greater than or equal to y. I've got an amazing program that satisfies that. It returns infinity. And it's equal to 1 of them. Thanks. Cool. Spec for Max. Related to the logical specifications are invariants. So this is one of the common applications of synthesis. It is a specific subcategory of logical specifications. Who is familiar with loop invariants? Most, not all. Okay. So if we want to prove this property, what we want to do to prove this property is we want to come up with a loop invariant. A loop invariant is something that is true when we enter the loop. It is true after every execution of the loop, and if we leave the loop, it is true and it implies that the property, this assertion here, is not violated. Is this property, is this assertion violated?
I think it's the opposite, like when you leave the negation.
No, the invariant is true when you leave the loop, and it implies that the property is true at the end.
You need the guard as well.
In
It's invariant to the negation of the guard. Implies,
yes,
Yeah. It's not there.
you would technically not need the guard if you have a loop without a guard, right? Like what you want to know is if I leave this loop at any point.
Okay.
Like this would still prove that property without the guard, right? It's just that putting the guard in it makes it slightly easier to find an invariant.
Sure. Please. Okay.
Like the assert is going to take effect during runtime, or is it like we can't statically know? I mean, we can statically generally know specification in assert. Like whatever you given, looking at the program statically, you can't know. I'm asking like, let's say the program is running, and that violates the thing, and is it going to take effect during the runtime? Just want to know like how does that work?
The assert would take effect during runtime if you happen to hit a trace that violated it. I don't want to run the program because the problem with running the program to check if the assertion is violated is I'm going to have to run it on all the possible inputs. And I don't know how long I'm going to have to run it for either, particularly because I only exit this loop when some arbitrary button is pressed, and I don't know where the button is and I don't know who presses it. So what I want to do is I want to find a loop invariant that allows me to prove that no matter that whenever I leave this loop, the invariant, the assertion is not violated.
Okay, this is specification like that.
So this is a specification. I want to find the invariant. So I've used init to be the initial conditions. Transition. I've used trans to say that the loop is being executed, and I've put the property in there. So I could substitute the actual code in for those functions, and then what I'm doing is looking for an invariant that satisfies this property. And if I can find this invariant, then I know that property is never violated. I could be mean and ask you to find the invariant, but I think it's on the next slide. So it's not on the next slide. Damn! Find the invariant. Any suggestions for the invariant?
A less equal B.
So I think A less than equal to B is part of it, but I don't think it's quite enough because I don't think that is inductive. Because I think if I have A less than equal to B and then I execute the loop, I think it would be possible with an arbitrary execution for that to then be violated. Imagine that you entered the loop on a random execution and you've got no idea about the initial conditions. So we're looking at the second line of the formula here.
0 is less than equal to A.
Sorry?
0 is less than equal to A.
I think what I actually need is A less than or equal to B. You're very close, but I also need to say that B is never negative. Because when I add, because eventually, I think I need to say that they're both negative. Because otherwise, when I add them together, I can end up reducing the size of B by adding negative. Okay. Reference programs. Someone mentioned this. Maybe you have an inefficient program, but it does what you want, and you want to find an efficient one. That's pretty easy. You can query it to get input-output pairs, and then we're back in the world of PDE. If your reference function is something that you can actually look at, then you might be able to get some other information out of it. Like you might be able to look at it and say, well, these operators are quite likely to appear. But the key thing is that you want input-output examples, and then we're back in the world of PDE. What appeared on this? Just a big circle that said these are all logical specs. Yes?
So why is it that you consider equivalent programs to be a subset of first-order logic, let's say, so in your Venn diagram? Right? Is it because you?
I consider everything to be a subset of. I consider these to be a subset of logical specifications because my actual spec is: does there exist a program P such that for all possible inputs it behaves exactly the same as my reference function, like my semantic spec, to be clear, like my spec about what the program should do. Is that okay?
Yeah, I was just curious if you could always write that as a quantifier-free first-order logic formula, because it's in the green circle.
Good point. If your program has loops in it, then you obviously can't write it as a quantifier-free first-order formula. So then we would have to move it outside of that circle. I am mostly considering programs where we fix the number of loops that we fix the unwindings for the number of loops. We also talked about natural language, which I'm not going to talk about because I don't think it's very interesting, but this is how you would get code from a large language model or how you get code from many machine learning things, natural language. I'm also not going to talk about reactive synthesis because it's sort of a tangential world of synthesis. Did I make a slide on it? I did not make a slide on it. So it's a tangential world of synthesis where you try to synthesize reactive systems. So you give your specifications a temporal logic formula, and you're essentially trying to come up with sort of machines represented as automata. I'm not talking about it because we've only got a couple of hours, and it would be impossible to teach you all of synthesis in a couple of hours. So that's what I decided to kill. I've also only considered semantic intent. We also need to talk about syntactic intent. So many times it's enough to just say, I want a program, the program should work. But a lot of the time we care about what the syntax of the program is as well. So this might be as simple as I care about the language it is in, but it could be It could be a lot more complicated than that. It could be that you want a specific, so if you want to program in a particular subset of a language, perhaps. So yesterday we saw some of the Hacker's Delight examples where you have calculations manipulating bit vectors, and it turns out if you do lots of bitwise operators, they're often faster than if you just do the normal calculation written out using regular operators. So there you would want to have some syntax that says, please do this using the weird bit vector operators. The other reason we care about syntax is because, and about restricting the syntax, is because the problem is in general very hard. We've got a massive space of possible programs and we want to shrink that space of possible programs. Okay, the classic way we would do this is we would give a context-free grammar. Familiarity with context-free grammars. Wave at me if you are familiar. Okay, so if you are not familiar with context-free grammars, so we've got a couple of non-terminal symbols, and each one of these is tells us what we can replace that non-terminal symbol with. So if our program returns an integer, our non-terminal symbol I is an integer, and we can replace it with x or y or 0 or 1, or we can replace it with an integer plus another integer. There is a format for program synthesis with a context-free grammar and a logical specification, and that is syntax-guided synthesis. There is a website, which I have put there. So this is what that format looks like. If you're familiar with SMTlib, it will look familiar. If you're not familiar with SMTlib, it's really hard to read, sorry. So should you want to play around with this kind of synthesis, there are tools that will do this, and there is a format that will do it. And I put the link here so you can do that in your own time. Be careful when you are searching for the website, because interestingly, the Cygus website has been cloned, and there's a copy of it which contains a weird link to some kind of financial trading spam site in the middle. So that is the correct link. So this is a Cygus file for max. I really like calculating the maximum of 2 numbers. This has our constraints that we had earlier. So implicitly, all of these constraints are implicitly conjoined together, and the specification is find the synth fun such that for all values for the declared variables, the conjunction of these constraints is true.
Why the problem of finding the maximum of 2 numbers interesting in the context of program synthesis? Like you mentioned it like several times.
It's not interesting, but it's very tangible.
Okay.
So if I give you arbitrary invariants, the specifications don't look as neat. This is mildly interesting because it requires you to enumerate a reasonably deep program. Like the program is not just like x plus y, and it's a specification that requires thinking about a little bit. Interestingly, one of the things that these kind of synthesizers are still not great at is if you start needing massive nested programs, if you start needing the maximum of 8 numbers, not great at it. We're not going to create a Cygus file for this and run it, but I've left you the command, so if you're curious, you can run it. I've put the -o Cygus on the end of the command, which will let it spit out a load of extra information about what it's doing, but that's not necessary. Okay, another way you can give syntactic constraints is sketching. So you provide basically a partial program and you put holes in it, and then you say, please find me something to go in the holes such that it satisfies the spec. The classic tool for this is Sketch. We're not really going to talk about Sketch because I had to pick one, and instead we're going to talk about Cygus. But if you have more of an idea about the skeleton of your program, and also if you hate the idea of writing in the Cygus interchange format, take a look at Sketch. Okay, have we captured our intent? Kind of? I think we've captured our intent. And I think I've taken 13 minutes to capture our intent. So the next question is, how do we find a program that matches the intent? Any ideas? Yes, hello.
So can I go back to the spec with Max?
Yes. Did I write it wrong?
No, you didn't. I'm just curious about a slightly different spec, which usually we use in mathematics, which is something like, if z is greater than x max y, then z is greater than x, and z is greater than y. It's a different spec. Is it just harder to work with, or is it?
If z is greater than x
If z
max.
is greater than x max y, then z is greater than x max y if and only if z is greater than x and z is greater than y. I think it's that way around.
Sorry, you're saying x max y, you mean max x y?
Sorry.
Oh.
Yes, I'm putting max in the middle. Sorry, max x y, yes.
That's the same spec, right?
Oh, I don't know. Right.
I
I didn't spot the z.
but z is the output. So you've introduced, okay, so if
So-
z is greater than,
Greater than or equal to max x y. So it's this if and only if z is greater than max. Sorry, z is greater than x, and z is greater than equal to y.
turns out I can't write z.
Yeah.
Okay.
And this is for,
Sorry, did you
know,
say Z is the output? As
Z.
in of X, Y?
Z is just an arbitrary number here.
yeah, it's for all
Um,
x. It's for all x.
So, I think that would work, but I think that would work.
The reason I'm kind of weirded out by this specification is that it's sort of not really included in the code in some sense. Like Z doesn't seem to appear. Doesn't
You
cause
would
problems.
have to, so you'd have to put Z as a declare var, so as a universally quantified variable. But there isn't anything that says you can't have universally quantified variables that are not included in the functions. So you can have universally quantified variables in your spec that are not used in a function application. That would be fine. So I think this would work. I've not tried it, but maybe in the break I'll try it. I think it would work. Like, theoretically that's allowed. Yeah.
I think the right-hand side constraint z and x equal to x or y.
Oh yeah, that does also need to happen. Thank you.
Z or
the last
Denise,
one.
do you?
Wait.
You do.
Wait, is that true?
It's not.
Well, hang on,
No.
because what I need is something that stops this function being.
The left-hand side said that z can be bigger than, so z can, x, y can be 1, 2, and z can be 3.
Z's allowed to be.
Yeah, z can be bigger than both x and y, whereas the right-hand side z can either be x or y. So I'm saying that if and only if in the middle doesn't quite hold anything.
Does that fix it?
I think what this is that the Z is like an arbitrary number bigger than the maximum.
Yeah, and we need to stop z from being.
But you don't.
Or Z could be the maximum upwards, and then
What
X, Y
what
as
this
well.
spec doesn't do is this doesn't stop me having.
And return an arbitrary number.
This doesn't stop me having max returning the bottom number of my data type.
well, that's the ordinary right?
It does. Because if max is the bottom, then you could have z be a tiny bit bigger than the bottom, and it would have to then be bigger than x and bigger than y. So
Yeah, that's the ordinary.
Oh, good point. I think this works. I think this works. We'll try it in the break. We'll try in the break and we'll come back after the break and we'll decide if it actually worked. Am I going forwards or backwards now? I regret talking about Max 2 now. I'm going to come back to this after the break and figure out an actual answer before, rather than just having an argument about whether this works or not. Okay, once we have a spec, we're going to need some way of actually finding a program in our space of possible programs. Thoughts? How are you going to do it if I'm just like, oh, I've given you a spec, solve this for me, please. Let's suppose that I've given you programming by example. So I've given you some input-output examples. I'm like, right, for the next hour, we're just going to build this. What are you going to build? Yeah, what's the stupid obvious answer? Most of
Which
Synth.
statement will build the, this is the
Okay, switch statement with the if this is the input, that's the output. That is the stupid obvious answer that if you don't give it if you don't give a syntactic, like a reasonable grammar in your problems, I will give you the stupid obvious answer. A lot of synthesis is the stupid obvious answers. Okay, I've given you a grammar. Now what are you going to do?
You're gonna enumerate all the programs?
Enumerate all the programs in the grammar. This is what we're doing in many different ways. Cool. First thing we're going to do is bottom-up search. So, given a grammar, here is a really stupid grammar. I am going to do, so bottom-up search, I am going to first find all of the programs, so I'm first finding all of the shortest programs. So what I do is I pick a production rule, and I see if I can get a complete program out of it. So I can. And then I pick the next production rule, and I keep doing this until, oh, this is one where I can't get a complete program out of it, so I think I'm done at this point. So I've gone through all of the production rules, and I've got all of the complete programs that I can get with just one production rule, and I put these in my big pool of programs. And then on the next iteration, what I'm going to do is I'm going to go through all the production rules, and I'm going to say, how many complete programs can I make with my production rule and programs from the pool? So on my next iteration, I hope I'm going to get some programs. So I've got this production rule that turns E into 1 again, so that just produces 1 again. Now I've got the one that turns E into 2, that produces 2 again. Now I've got the one that turns E into E plus E, so now I go and I look in my program pool, and I go, oh, I'm allowed to use 1 and 2 as my expressions E, so I do all of the ways I can combine 1 and 2 with that production rule, and I get a bunch more programs. And I keep repeating this until I find a program that works for all my input-output examples.
Given a context-free grammar, does there exist any algorithm that would enumerate all the, I mean, at some point I would be able to get a string in the string generator by the grammar. Is there any such algorithm that works?
In a context-free grammar, is there an algorithm that enumerates all the programs?
All the, so basically you want to generate all the strings produced by the grammar, right?
Yes.
Yeah, so like, is it like, given an arbitrary context-free grammar, is it like possible to do that? It doesn't have to terminate, but like at some point I should be able to get.
Context-free grammars can express an infinite number of programs, or an infinite number of strings. So in theory, so if you have a, so no, because there's an infinite number of strings.
Yeah, but at some point, I mean, is it even enumerable? Like at some point I would be able to get, given a string, at some point I would be able, just like enumerating natural numbers. Like at some point I would be able to get it something.
Yes, so this enumerates through, so this algorithm will enumerate through all the strings in your, all the programs in your grammar, starting shortest first.
Okay.
So on the first iteration, we do all of the programs you can get with one production rule. On the second iteration, we do all the programs you can get with a depth 2, and so on. And so if you have a program of depth n, and you run this for n iterations, you will have that program in your program pool at the end.
Okay.
Assuming that your laptop has not run out of memory.
Okay.
Because this has obvious issues that we have exponential growth, and your laptop runs out of memory. Yes. That's some pseudocode. Okay, I'm going to come back to the pseudocode, but I'm also now going to, so this is one, so I'm going to show you what's in the simple synth repository, and then possibly we're going to spend some time implementing bottom-up enumeration because it's very straightforward. So, okay, I'm also going to turn off Copilot, I think, if I can turn him off. Okay. So, if you are in the simple synth repository and you have run Python main.py, what you should get printed out is you should get something that says, I'm a program synthesizer and I don't work. It should then tell you that it's got a simple program by example, that it can't find any solution, and then it also tell you that we haven't implemented some of the other stuff that we're going to implement later. The relevant bits that you will need to look at, So the first thing we care about is the specification. So if you go into utils, you will see that we have a simple specification where we've just got a list of examples. If you look in main, in the PBE function, you can see how we create a specification. So we've just got X and Y, and we give the input values. You can also see how we create a grammar. I have fudged this a bit because I didn't want to build a parser, and I didn't want to, I wanted to use the simplest possible representation for your programs. So what I've used is I've used the Z3 solver representations, and your grammar, you can only add variables and binary operations and unary operations. I haven't let you define any production rules that aren't just apply this binary operation or apply this unary operation. We then have a class called synthesis, which has a function called search. And there's a lot of code in here that you don't need to care about. What you need to care about is the search function, which currently, for each depth iteration, it says generate the next expression, and this doesn't do anything at the moment, and it does need to do something. And ideally, you would do something in the generate next expressions box. How do we feel about doing that? I have given you a bunch of utils about applying a binary operation and applying a unary operation. So I think we could implement the basic, each iteration of the bottom-up synthesis in there. Also, if you can't be bothered, you could go to the Git repo and you could check out the branch that says completed bottom-up enumeration or something along those lines, and then you could just pretend that you did it. In this repo, if there is ever a thing that says to do, that's where you need to fill something in. And it's 9:45, and so I think, anyway, we'll think about this for 10 minutes. I'll wander around. If no one is doing it or everyone is bored, then we'll just show you the solution. If people are doing it and having fun and they've still got stuff to do, then we'll stop. Then we'll continue. Do you want the pseudocode on the screens, or do you want the bullet points with the blobs? Let me. You can have this, or you can have this. Which one do you want? This one. Okay. Okay. I'm going to briefly turn off my microphone, and I'm going to, yeah. No.
So imagine then once we get applied with the second one, we would want to use this and not have to pick a program.
Probably, yeah. Yeah, it's a list because.
Right? And then you go to the second one. So it's like you end up with 1 and 2, right? So then you just, what was the same, you just have it, right?
I make no claims about the efficiency of this code. So in the, have you got the Git? Yeah, so if you go into synthesis.search, there's a function called search in synthesis. Yes. So in there, there's a function called generate next expressions, and that currently doesn't do anything. So what that should do is that should do this. It should go through the grammar, and it should generate some of the next expressions from the program call. So there is a program call defined. So what you want to do is you want to go through the grammar, generate all possible complete programs for every rule in the grammar. So the grammar.
Can I just get someone arbitrary
So if you open utils.py, there's a grammar defined there, and it's just a list of binary operators, unary operators, and constants and variables.
Oh, we have a specific grammar here.
Yes.
Oh, from that, like for that grammar, we have to like not some arbitrary collection.
So that grammar specifically.
Okay.
So you want to take the operator. In the first iteration, you know that the only complete programs you can generate are the constants and the variables in that grammar. So you can just, if we're on iteration 1, you know you can just put those in the program. On iteration 2, you know that you can take the unary operators and the binary operators, and you can combine them with anything in the program.
Oh, it's just some specific grammar for that grammar. I have to like write.
Yeah. So the grammar is the grammar class lets you define a grammar, and you want to do it for the grammar defined in a grammar class.
Oh. Yeah. I will have it.
Cool. The answers are on. So if you want more hints, go on the Git repo and look at the next completed one. There's a branch with the solutions.
Generally, the next question is only one step, right? For each step.
Try that. I did, and that was terrible. Turns out if you let ChatGPT generate an entire, if you ask it to generate an entire workspace for a universal synthesizer, it will have a pretty good go. It will produce an entire workspace that does some synthesis, but it's very hard to know what it's doing.
It's like I work with the React like things in outside. I work with some things off. It looks like
It's finally generated something small, but it generated the entire workspace. So like there are pages of code in it and tests and like GitHub actions and stuff. Now you've thrown a curveball there, and now like, on the spot reasoning about specifications is hard. Just with loads of specs, right? And for example, it's so much easier. Yeah. I'm slightly worried that you mispitched the amount of code in this. And I can't really do like programmer. Well, I guess I could have done programmer, but like that's not. And like you can't really do like program along and use program synthesizers. Basically, there all you're doing is writing specs. In the brain, I'm going to write that spec and see if I can solve it.
not just
Writing programs for a program synthesis tutorial is so meta. We are the program synthesizers right now.
Yes, I mean, my whole career is writing code for Python. Right? I can't decide how to duplicate this. The amount of things are left in the fill in the blanks too powerful, too sparse, or give me feedback because this will get iterated.
I think also the thing is we need to know about the rest of the program before because there's a lot of calling other functions.
Yeah.
So written above and below. So
Could use some reference
familiar with
for
the repository a little bit more before
Yeah.
this class.
Just sort of question about the context of using the grammar that's been defined and not implemented into it.
It's
Because
that is the answer. It's about
we're just mashing strings together.
yes, you're mashing strings together, and then Z3 converts them into expressions. You are just mashing strings together. And I left some of the apply apply binary operator in there to show that you're just mashing strings together.
Yeah, because I think it's easy to sort of overcomplicate Android.
Yes,
Yeah, look.
just mashing strings together.
Right now all the libraries and everything. It's like I'm supposed to write a program or algorithm. Like even I have a context free grammar, I'm supposed to generate all the possible strings in them.
So what you want is you want generate next expression to so
there is a again, watch out. One day something.
could you open synthesize.py for me, please? I am not an Emacs person. Right, so generate next expressions should, so what happens is search calls, so for each depth it calls generate next expressions, and that should generate the next layer of expression reproduction rules. The way I would do that is I would use apply binary operation and apply unary operation. So all of your operators are applying it. So if I call this, so say I've got two programs in the pool, and I've only got this one, I've only got this operator plus in my grammar. What I would do is I would say for all my operators in the grammar, apply binary operator on my two programs in the pool. And then that would return the program, and I would put that in the pool.
Oh, okay. So I don't have to like think how to generate something. I just have to like use the
We're
operators.
just mashing programs, so we're just mashing operators and operands together.
Okay.
Like there's nothing smart about this.
Making compound things from small things. Just
Exactly.
And
Exactly.
you only have like
The
four.
first thing you want to do is fill the pool with the small things,
Okay.
and then you want to mash them together with the operators,
I don't
and
have to
keep
like
filling the
generate.
pool with the bigger things. And then at each iteration, mash some more stuff together with the operators, and we're just smashing strings together at this point.
Okay.
And apply binary operation and apply unary operation will do the smashing for you.
So do we have already?
Self-developed, so they've done. So what that becomes.
Right. Okay. How close has anybody got to having something that sort of enumerates stuff? What I think I'm going to do is I think I'm going to show you what I did, and then we're probably going to talk about some of the next algorithms. So, can I make this go away? Yes. Okay, so if you look on the Git repo, all the answers are on the Git repo. I'm afraid none of synthesis is as complicated as I would like it to be, and we really are just smashing together strings at this point. So what I did when I implemented this is the first thing I did was I said, oh, if the program pool is empty, that means I'm on my first iteration. So I'm going to put the constants and the variables in the program pool because that's nice and easy. I know that I can do those with one production rule. And then what I do, if the program pool is not empty, then what I'm doing is I'm iterating through all combinations of things in the program pool, and then I am smashing them together with a binary operator, and I am also I'm also putting the unary operator on them. So I iterate through all pairs that I can get, and I smash them together with all the binary operators I've got in my grammar. Sadly, it's all just that simple. And the other thing I left incomplete is apply binary operation. I only implemented one of the binary operations for you, so if you had found that function and tried to use it, it would have only worked for plus, so you needed to add the other binary operations in there. And if you'd run it now, it would have gone through a lot of programs, and it would have hopefully eventually have found a solution, which was x plus y, because that's what I put as the spec, and it would have apparently explored 584 programs to get there, which feels like quite a lot of programs. Are there any questions? Did I make that code too incomprehensible? No questions. So that's either a yes or that might be a yes, it was too incomprehensible.
We knew what we wanted to do, we didn't just quite know how to express it. But,
Okay.
we're getting there, so thank you.
Is it now clearer how you would express it?
Very much so, yeah.
Okay, that's reassuring. Okay, I had slides. Where are my slides? Problems with that? It took me 584 programs to find a really simple program. Any suggestions for what I was doing that was stupid? Apart from using a list instead of a set for the list of programs, which meant that I stored programs that were like syntactically identical. I would have had duplicates. Is there anything else I could have done to improve that? Along the same lines, yeah?
Yeah, a lot of them were semantically identical as well, even if they were syntactically.
Yeah, I also had some programs that were semantically identical. And there are some things I could have done to like tweak the grammar or the way I was handling the grammar to avoid that. Right? I know if I've got A plus B, I don't need B plus A because I know that they are the same. I'm going to tell you about something that is even better than doing that, which is observational equivalence, which is better than having to check the full equivalence, because for full equivalence I would either have to ask an SMT solver if the two programs are equivalent, which is expensive, or I would have to encode a bunch of rules that tell me when two programs are equivalent. So sometimes programs are not equivalent in general, but under a programming by example specification, they are equivalent under all of my examples, and so I can consider them to be equivalent. So this only works for PBE, but if you consider that I've got a bunch of, suppose I've got abs in my grammar, but all of my inputs are greater than 0, I don't need to have abs in my grammar because it's equivalent to just not having it there. Like abs x is x. there are many cases where there are many similar cases where some of these programs you put in your pool, they are going to behave the same on the inputs in your specification, and so we can consider them to just be the same, and we can drop one of them.
So, I have a question on the earlier thing. Let's say we have some CFG for example, let's say some functional language, like some AST for a language.
Yeah.
And so you are just enumerating it, maybe testing it. The possibility that that it can go infinite at some point, like for some specific program, and it gets stuck there. Is there any bound on like you, for example, I understand is that you generate one thing, you check it, and then go to and check it. For example, there can some program expression that could go on infinite and just.
Okay, so the question is, how do I test programs if they might run forever?
Yes.
The answer is, don't enumerate programs that might run forever. I don't have loops in this language.
Okay.
As soon as you have loops in the language, this gets harder because you have to have some way of testing the programs that have loops, which means that you probably need to have loop invariants.
Okay, so yeah, that's why
Right.
like one of the earlier questions you're talking about all things that can be expressed in the first order. So one of the earlier questions that you mentioned that like in the Venn diagram,
Yes.
you put everything in the
I
thing
put
of first
things.
order.
I put the specs in the first order. I should probably say that I want you to be synthesizing loop-free programs
Okay.
here. There are techniques for synthesizing programs that have loops and programs with recursion, but I'm not talking about them.
Okay.
Mainly because testing them, as you've correctly pointed out, becomes harder because you need to have some way of like checking a program that contains a loop, which is obviously undecidable.
Okay.
Yes.
Yes.
Observation equivalence. You can remove two things you can remove one of your programs if it behaves the same as another program in the pool, because we can build up. If at any point we were going to use that program to build up another program, we can just use the one that was observation equivalent to it. What this means is it needs to have context-independent equivalence. So it means that if we have two expressions, if we evaluate E1 and E2 on an input in our spec, then we know that evaluating any expression that is bigger than that contains E1 and E2, if those two expressions are the same, then it will evaluate to be the same. So what this means is if I had x plus, so as an example, if I had x plus 1 and I had abs of x plus 1, they evaluate to be the same, because I know that abs x and x were the same, because they behave the same on my inputs. It's just a clever way of pruning. Questions about observation equivalence? Yes?
Can we use that to go back the other way? So it looks like these programs which are semantically different but observation equal under your examples
Yes.
might point to an ambiguity in the specification.
Yeah, you could try and do that. I don't know whether they would point to a meaningful ambiguity in the specification. The question was, if you have two programs that are observationally equivalent, does that point to an issue with your spec? And so should you be going back to the user to say, by the way, these two programs are the same. Did you mean that? Should you have some other inputs, please? I can see that might be a good way of pointing out holes in the spec. As far as I know, I don't think anyone has done that. But yeah, I'll have to get back to you. Okay. Does the idea of implementing observation equivalence in the enumerative synthesizer, does that seem terrible? One vote for yes, that seems terrible. We could take a look at the code and walk through the code I added line by line, or you could have a go yourselves, starting from the branch that has the completed enumerative synthesizer. We can decide. Votes for we look at the code on the screen. Votes for I have a go, and then we look at the code on the screen. I mean, that's actually about equal. Okay, fine. So if you want to have a go at it, now is your time to have a go at it. If you don't want to have a go at it, now is your time to sit and chat or look through the GitHub repo or like do whatever you like, and then we'll come back and we'll put it on the screen. I'm not going to force you to try and do the coding, but if you want to have a go at it, we'll have a look at it now, and I will come back in 6 minutes. I will show you where I think you should be looking though. So the bits of useful information, there's a function called check PBE with observational equivalence. You're going to have to do something here, and I will tell you that if you go to verification.py, you want to look at verify PBE program, and you want to see what that's doing, because that should be checking against an example, and you want to store the output from the example. So the two functions you want to look at, you want to look at check example in verify.py, and you want to look at check with observation equivalence in synthesis.py.
But maybe some of them are smaller than the others or faster than the others, or do more or less memory?
Do we lose anything by removing these programs because they might be smaller or faster or use less memory? Yes. If you cared about the memory consumption of if you cared about like the memory footprint of your program, or you cared about the runtime, it would be a good idea when you are filtering these programs to also have looked at their runtime. So sometimes people care. For most synthesis applications, they tend not to be guided by things like speed of program. There are some where they are. But so most synthesis applications where you are saying let's find something that is faster, you're often saying that you're often finding that things are faster because of the grammar that you've given. So one of the easy ways of making things faster is to find a nice DSL that someone's written a super fast compiler for that compiles your code super efficiently, and then you just need to lift from their language to that fast language.
Can I ask a new question, just really well interpreted?
Yes.
So before LLMs entered the picture,
Yes.
how good was the very cutting edge of synthesis system?
Before LLMs entered the picture, how good was the cutting edge of synthesis? So things like the enumerative techniques I'm telling you about are okay for small cases. So if you have a well-defined grammar, these can be really effective and much more effective than something like an LLM, because an LLM is not very good at finding like precise programs. If you want large blocks of code, obviously an LLM is much better, although how do you tell it to give you correct code is an open question. Prior to LLMs, the cutting edge of synthesis was definitely still generating very small amounts of code. But it would be things where you've got, say, a neural network that is trained to give you like sketches that then you're completing with enumeration. So there would definitely be some machine learning in there for the actually scalable stuff. But half the trick with synthesis is finding an application that fits well. Just like complete my programming exercises for my coursework is not really feasible.
How has the landscape shifted since the arrival of LLMs?
Since the arrival of LLMs, everybody is...
Some people were worried that this would actually kill synthesis, but it doesn't seem to happen. It benefits organizations.
I don't think LLMs are going to kill formal program synthesis, because I think the answer to using LLMs is always going to be they have to be integrated into some kind of loop that has some kind of feedback, and how you give feedback to a search is essentially what synthesis is. Like, very few of the synthesis algorithms are something where like, oh wow, that is super clever. Like, there's a couple, but most of them are search with some feedback, and it's just about how you do the search. guess LLMs they've changed the landscape, but I don't think they've made synthesis, I think they've made synthesis more relevant rather than less relevant. But I have to say that because I like being employed.
Are you exploring the best practice intelligence?
We have done some stuff with using LLMs to guide enumerative synthesis. We have just got a funded project from DARPA which is lifting C to Rust, and that is going to involve LLMs, and it's going, but that's necessarily going to have to involve, so everyone, they had the opening meeting for the Tractor project and everyone talked about what they were going to do. Everyone's doing the same thing. The same thing is finding ways to combine results from LLMs, finding ways to get like different LLMs to work together to produce a complete solution, and finding ways to give feedback to the LLMs. Are there ways where you can sort of fix some of it with enumerative synthesis, where it's an where it's a problem that enumerative synthesis is well suited to? Yeah. I didn't want to be an LLM person, it just happened to me.
Basically, we do have some specification in some structural language where they select what they want to do. In some, whatever that can be expressed using structural some model language. And we are writing and we are generating programs that are loop free.
Yes.
So you can't have higher order functions like the function. So essentially, you have to at the end check some equivalence, which you can't in general do if you have functions. Like for example, if you return a function, you can't just generate it. Basically, it could be some programs can generate check it. So for example, if some data you could actually check. But let's say if I have something that returns a function, I can't check their meaning. In general.
In general, you can't check if two arbitrary programs are equivalent. In practice, so if your specification involves checking a program in loops, you're going to have to require your synthesis to also generate the loop invariants that let you check it. Or you're going to have to make compromises, and you're going to have to say, I am willing to do that, I am willing to synthesize something that is equivalent, and I checked it up to a bound of, you can check up to a certain unwinding of a loop, or a certain unwinding of a recursion, and that's fine. And you just have to accept those compromises.
Yeah. So there are specified limitations by which I operate, something like that. Like for example, if you have loops, then I would say let's say you do 100 iterations.
Yeah, the best option if you have loops is to also say synthesizer, you have to come up with a program and a loop invariant for that program, and then I can verify the program. But if you can't do that, then you just say, okay, a fixed bound is fine.
Okay.
My favorite word once it doesn't decide whether something is added to the program, will it just decide whether it's used?
I think what Amazon does is just post hardware. So they are going to probably give OpenAI not more hardware to use their end users. They are not really working with their own chat models. Everything's going.
Okay. Right. We've in the compromise position. We're now going to talk through the code that I would have added if I'd been live coding this. So one of the things that you need to do is make sure the checker is storing the output of the program when it checks it. I realised that I probably should have completed this bit for you because that was kind of difficult given that you're probably not familiar with the Z3 Python interface. So one of the things I've done is I've stored the outputs of every program. When I've checked it against the input examples, I've also made sure I've stored the outputs, in a list. Then what I've done is when I'm adding a program, I basically check to see if that output is in my list of examples, and if that output is not in my list of stored output examples, I'm like, oh, that must be a fresh program. Now I can add that fresh program to my pool of programs, and if the output was already there, I don't do it. So it was a relatively small amount of code. While I check out the branch with this code in, any guesses as to how much that would have helped? Oh, the other thing that I had to do was also add the specification into the function that did observation, like that called it. But so yeah, the other thing I had to do was actually add a spec into here, but that was not interesting code. Okay, any guesses as to the improvement? 10 programs. So we're saying 574 programs. Any ups on 10? No. 11. Yep. Cool. So we have to run both of them, which I didn't really think through. Okay. It does seem to be taking a while. 360. And the size of the program pool is 108. So we have massively trimmed that because, so we're not even searching for very deep programs here, but the key for the trimming is that if you can remove one program from the program pool early on, that massively trims the number of programs you generate in the next iteration. So you're basically taming this exponential growth. Your growth is still exponential, so if you need very long programs, you're still going to run out of memory, but we have made a substantial improvement on that. Okay, what should I do with, there's the clicky thing. Any questions? Okay, other ways to search. You could also do top-down search. We're not going to implement top-down search. So top-down, so what we did was bottom-up, which does the shortest programs first. This is really good if you want a short program. If you want a long program, you're going to run out of memory. So we could also do top-down enumeration, where, so we can represent the space of programs as a tree. So we're starting with the start symbol of our grammar at the top, and then every box here is a partial program where we've applied a production rule, and then eventually in this tree you get to complete programs, which are the green leaves. And so top-down enumeration searches this tree. So we initialize with the start symbol, and then we repeatedly choose a production rule to replace the leftmost non-terminal in the current expression. This choice would probably be just pick the first one if we're implementing it naively. Maybe there's heuristics. So in this instance, we've picked the production rule that replaces E with C, and then we pick we look at what production rules we've got, we pick the next one until we get a complete program, or until we hit a depth limit, because there is obviously a problem here that we could just keep going forever, because there is an infinite number of programs of the form E plus E plus E plus E plus E plus E plus E. Yeah. So, top-down search. Yes, question.
How do you come up with these handwritten heuristics?
How do I come up with these handwritten heuristics? So, that's a very good question, and unfortunately the magic of making program synthesis work is often coming up with handwritten heuristics. So, the naive top-down search will just pick the leftmost, and then you'll mark things that you visited. The handwritten heuristics could come from if I've got a reference program and I'm synthesizing something that's more efficient than it, I might look at the operators that appear in it. I could train a machine learning model to sort of try to predict which operators are likely to appear in it based on the spec. I could do some reinforcement learning and I could get rewards based on how many counterexamples my programs satisfy. But the disappointing answer is it's hard. And often when people make program synthesis work, the magic is for sort of big scale applications, the magic is that they've been able to come up with these heuristics. Yeah. Sadly, there is never a free lunch, except at summer schools. There appears to be a free lunch here. Okay.
So what step process was the
why would I do this?
why don't you try like press search across the tree?
Oh, well, you could.
Yeah.
You could, but if you're doing a breadth first, so if you're doing a breadth first, you're basically doing bottom-up enumeration, right? Or you're having to store all of your partial programs in your breadth first search, which is another thing you can do. You can also do an A-star search where you store all your partial programs and then you give them a score and you pick the ones with the best score. Yes. I will say that most synthesizers are doing bottom-up search, which is why we spent more time on that. But you will sometimes find that bottom-up is just impractical if you if the grammar is too sort of broad. Some synthesizers are doing something completely different, which is constraint-based synthesis. Who is familiar with SMT solvers? Okay, so SMT solver, you can give it a formula and you can say, please find me an assignment to any 3 variables in this formula that makes the formula true. That's all you need to know for this. So with constraint-based synthesis, we take an SMT solver and we try and ask an SMT solver to give us a valid program. So the query that we want to ask the SMT solver is, does there exist a program that satisfies the specification and is in the language of my grammar? And that's the hard thing to encode in an SMT formula, and I'm going to tell you how you can do that. The TLDR of how we do it is that we're going to fix the length of programs in the grammar, and we're going to create some variables where when you select, when you pick an assignment to those variables, you're picking a program. I'm going to show you what that looks like. It gets messy. So, yes, question?
No.
Okay.
I was just doing calculation with my hand.
Okay. So let's suppose that I'm only encoding, that I only want to look at all the programs of length 1. So I want to create a formula that says, does there exist an F that satisfies my semantic spec and also is one of these programs in this grammar? I can do that fairly simply, right? So what I can do is I create a formula that's basically saying, so I need a number of selector variables, which I've used B for, which let you pick between these programs. So I create a formula that basically says, if B2 is true, then you are a program that returns X. If B1 is true, you're a program that returns Y. B0 is true, then you return 0, and otherwise you return 1. I realise this is not the most efficient way of doing that selection in terms of the number of variables. In practice, solvers don't necessarily do it in the most efficient way. When we built one of these, it turned out that the effort to make it do it in the most efficient way, where you had precisely the number of assignments to the Boolean variables that enabled the number of programs you had, it turns out that wasn't worth it, and it was much more straightforward to do it like this. As a formula, I'm going to use this notation. So the question mark is the is if then else notation. So, oh no, that's the pen I can't use. I've been defeated by all the pens. A question mark, B colon C is the same as if A, return B, else return C. So that's what our formula looks like. And then what we do is so this formula is now the formula for our program. We embed that into the specification in place of F. So we've taken the F's that we had in F, x1, y1 equals z1, and x2, y2 equals z2, and we've embedded them into this formula here. And now we can just give that to an SMT solver. So x1 and y1 are an input example, z1 is the corresponding output example. We can now just ask an SMT solver to find the Boolean variables, and then it tells us what program we have. Simple? Straightforward? No one looks too confused? Okay, program of length 2. What I'm going to do is I'm going to encode this like instructions. So think of the bottom-up enumeration. I've got a formula for the program of length 1. I'm now going to create a formula for the program of length 2. So my program of length 2, I'm allowing that to be the previous program plus itself, or x, or y, or 0, or 1. and I create these two programs effectively, and then I get this formula. Do I have highlights on this one? Yeah, so then when I embed this into the specification, I get something absolutely mad that looks like this. This is the formula for a program of length 2 with 2 input-output examples. So I assume we're starting to see some obvious issues here. The more input-output examples you have, the bigger the formula gets. The longer your program is, the bigger the formula gets. Yes. So the main issue is the formula gets big. But this is how Sketch works, which is a tool that finds assignments to holes in your programs. And this method of synthesis is something that we've implemented and found very good for like bit vector manipulations, but it doesn't scale very well to long programs or lots of examples.
So this BC, I mean BI range over Boolean, right?
These are Booleans, yes.
Okay, and what does this question mark mean?
So this is if, so the question mark is the notation for if something, then something else. A question mark, B colon C is the same as writing, if A is true, then do B, otherwise C.
Oh, yeah. Ternary notation.
Yeah. Okay, there's some other search methods that I haven't talked about, but I'm telling you that they exist so that you know they exist. And I think now is time for a break. When we come back, we're going to find out what we do when we don't have just PDE. Please go and drink coffee. Did anybody have any thoughts that require addressing during the break? Okay, good. Right, what if your specification isn't just PBE? I'm bored of PBE, no matter how much Guy likes it. We're now going to look at things that are not just input-output examples. Can you ask me that question you asked much earlier? You put your hand up and you said something like, what about if we had... Can you remember what you asked?
I suggested a trivial solution, probably, which was basically, what if we guessed a random program and asked a SAT solver, why is this random program not the correct program, and it gives a counterexample, and we ask, now we train a machine learning model to meet that one, or again a SAT solver to meet that one, and then we again ask them, why does the program not correct again, until it gives the correct program.
Cool, thank you. So, what if we just guessed a program and then asked a SAT solver why that program is wrong, and then used the answer to try and guide our search? Now we've reached CGIS. Okay, I'm going to step through this, and then I'm going to give you a terrible analogy, and then we're maybe going to implement it, unless everybody looks like they've really had enough of looking at code. In CGIS, I have, also I don't know if you pronounce it CGIS or CGIS. I've always gone with CGIS, but I don't know. I'm going to go with a hard G because it's guided, but then I've also realised that that should be KeyGIS because counterexample also has a hard C. So. Okay, we have a synthesizer and a verifier. This is the specification that we had before. So we want to find a program P that's such that for all X, some formula holds. Yeah, got a guesser and a checker, essentially. That's how you can think of CGIS. So we start off, so I've got this list xi, which I'm going to say is the list of counterexamples that I have received so far. I'm going to start off with no counterexamples, so I'm just going to be asking a synthesizer to find a program that works for no counterexamples, for an empty set of counterexamples. So it's going to give me a random program. I'm going to give that to the verifier, and then what I'm going to do is I'm going to ask the verifier, is there an input for which this program didn't work? And that means I'm going to flip around the specification, and I'm going to say, does there exist an X such that the negation of the formula is true? assuming I have substituted in my implementation for P into the formula. So my implementation here is P star. If it says unsat, then I'm done. I can just return my program. There were no counterexamples. Great, perfect. If it says sat, it gives me a counterexample. That gets added to my my list of counterexamples, and then on the next iteration, I want to find a program that works for those counterexamples. Also, the synthesizer, you already know how to find a program that works for a short list of counterexamples because you already know how to build a synthesizer that works for a short list of examples. So what you will do is this synthesizer will be implemented using one of the search methods that we talked about, except that instead of checking it against a series of input-output examples, it will be checking that for a couple of specific counterexamples, this specification is true. And that's a much easier check than checking if a program is correct against the entire specification. So if I do this for Max, so we previously tried to write an input-output specification for Max, and we realized there were a lot of edge cases we needed to handle, and it got quite cumbersome. So if I instead have my logical specification, what happens, so my first guess is X. I think that's a good program. It's also a very short program, so I found it very quickly. And then I get a counterexample that says this doesn't work when X is 1 and Y is 2, obviously, because Y is bigger than X. So then I'm like, oh, I've got one counterexample. What program works for the one counterexample I've seen so far? Y works for that, right? So I return Y as my guesser. And my checker then says, but what about when X is 2 and Y is 1? So now I've got two counterexamples. So now I have to find a program that works for both of these two counterexamples. And coincidentally, because I wrote the order that we find these programs in, I find the actual solution. So we get there very quickly with Max. Potentially we could have taken more iterations.
I'm pretty sure I might be pedantic, but there's a suffix I that, like, is that a typo? Like for all xi?
No, so my synthesizer, so xi are the counterexamples. I could have put that on the slide. So the synthesizer is finding a program that works for all the counterexamples so far. So at this iteration, he's not got any counterexamples to work with. Here, he's trying to find a program that works for this counterexample. By the time we've got to the third iteration, we're trying to find a program that works for both of these counterexamples. My notation's a bit shoddy, sorry about that.
Yeah, I was just wondering, what's the X inside Sigma? Like, is it like, so where is it, the X bound? Like the for all xi?
So this is a specific list. So what this should actually say is for all xi in the list, and then have the list of counterexamples.
Okay.
So this is limited to this specific list. I'm sorry about my notation. Whereas here, this is just any x. How are we checking things? So before, when we were checking against input-output examples, I don't know if anyone actually looked at the checker in the Python code. So what we could have done when we were checking against input-output examples is we could have just executed the code. I could have built an interpreter and then executed the code and found out what the output was and then compared it to the output example. I didn't do that because I'm lazy. What I actually did was I put it into an SMT solver because I didn't want to build an interpreter. But what we're going to have to do now is we're absolutely going to have to use an SMT solver because we need to now check against this arbitrary formula. There's no point asking you to negate the formula for Max. There you are. Did I negate that? Oh, there we are. Yes, but this is just the negation of the formula. So you're just saying, please don't check whether that's correct or not. I did this on the train. Is it correct?
I don't know, I'm not checking.
I mean, if I had this formula, it would be much easier to negate. Oh, I tried this, by the way, this works. VSS25, which is a syntax-guided synthesizer, can find a solution to this just as quickly as the other specification. Yes, so we asked an SMT solver to find a counterexample for us. The guesser, any of the previous search techniques. That works absolutely fine, but now we have to check against the counterexamples rather than the full spec. So to check against the counterexamples, we take the formula and we just replace the universally quantified variables with the specific counterexamples. Yes. So I don't think you need the pseudocode. I do think you're going to hate this though. Okay. Do you want me to step through the changes I've made to the repo to make it do CGuess? Or do you want to look at the repo and then see how you feel about it? Votes for I step through it on the screen. Votes for we look at it for 5 minutes and then I step through it. Okay, you get 5 minutes to look at it and then I'll step through it. 5 minutes is not long enough to make the changes. I will tell you that the bit you need to be looking at, you need to look at, so there are two things that you would need to do. So the first thing is that in the verifier, I believe I've written a code for you to verify a logical program, but I think I was mean and I don't think I wrote the code for you to verify against the counterexample. I think that's the hardest bit to implement. So yeah, you would have a look at how to do that based on how to verify the logical program. And then what you would do is you would implement a CGuess loop in here. Somewhere about here, you're going to have this loop that calls the synthesizer and calls the verifier. If you wanted to do the quick bit of this, you would go to the GitHub repo and you would copy and paste the verifying stuff, and then you would just implement the CGuess loop. The CGuess loop should be the most straightforward bit. I will leave you for 5 minutes, which is definitely not long enough to do it, but it's maybe long enough that you can have a look before I give you the answers. So you want to negate sigma, and then you want to say, does there exist an X that violates sigma? No, because negating the whole, yeah. So you're looking for a counterexample that violates the first. So what you want to know is, so if does there exist an F for all X sigma is true, then you've got a valid program. So what you want to do is you want to find a counterexample that demonstrates that that's not true. So you're looking for the one assignment to X that violates sigma. But you want the assignment, so does not exist means that the SMT formula is going to have to basically instantiate the universal quantifier. You don't want that, you want it to find the single assignment and give you the assignment. So you have to negate it, split it to give you the counterexample. Negation just of the sigma, yeah. Negation of the quantifier rebit. Because otherwise what the SMT solver would do is it would just say this is unsat, but it wouldn't tell you why, because it doesn't. I guess you could ask it for the unsat call, but then you'd have to extract the assignment from the unsat call. Okay. Guys, why are you frowning? Okay, fine. You're the one person who's not allowed to be frowning at this. If you're frowning, that makes me think I made a mistake in my code. Okay. Right, so I don't know if you've had a chance to look at what's in there and what you would have changed, but if you went to the Git repo and snuck a look at the solutions, so what you would have needed to have changed, so the first thing you would have done is you would have implemented something that can check your program against the counterexamples rather than against the input-output examples. So this, I've used D3, and so what we're doing is we're substituting the candidate program into the specification, and then what we're doing is for every counterexample, we are substituting the counterexample into the specification as well. So this gets us the full formula that says, for counterexample 1, is my implementation correct? For counterexample 2, is my implementation correct? Then the main actual thing that you would have done is built a CGIS loop here. CGIS loops, surprisingly simple. So the synthesizer takes in the counterexamples. I'd already implemented that bit. I don't know if you'd spotted that it already had the ability to have counterexamples. The synthesizer search, that's using the same search function that we had before, so that's using bottom-up enumeration. And then the verifier is verifying the program, and this is just iterating through. So each time the synthesizer makes a guess, the verifier verifies it and passes a counterexample back to the synthesizer. This is not the most efficient implementation for a couple of reasons. One of them is I'm resetting the synthesizer every iteration because I couldn't be bothered to make the synthesizer have state to figure out how far through the enumeration it had got. If you were actually implementing this, you would make sure it kept state. Yeah, so, oh, that wasn't what I wanted. What I wanted was VS Code. I believe this works. don't know if this is quicker than the standard enumeration we had with observational equivalence, because we are searching for, so I gave it a very, very simple logical spec, which was just to find the function x plus y so that we could compare it directly to the previous ones. But it did find the correct program, and it only had to use the verifier 3 times before, like it only had to verify against the full spec 3 times. Questions? Okay, so Series is a little bit like a game that you sometimes play as kids. So one of you thinks of a thing, and the other person tries to guess what it is by asking questions. So you ask questions, and the person that has thought of the thing, they answer yes or no. This is a little bit like CGIS. So we sort of have someone that's trying to synthesize a solution, and we sort of have someone that is an oracle or a checker or the verifier. There are obvious issues with this analogy, though, because actually how CGIS works is a little bit more like this. So we're not asking, the guesser is not asking questions to refine the search space, it's just naming specific examples, and the verifier is just giving yes or no. I mean, I guess it's giving a little bit more information than that, but it's really only giving a single input-output example. So this would be a really stupid way to play the game, right? You can think of this as being like you having a really great research idea and your supervisor trying to figure out what it is and asking really stupid questions. You know, you have this great idea and your supervisor is just like, but isn't this this? Isn't this this? It's never that, is it? So, yeah. CGIS sometimes is kind of stupid, and you might think that CGIS doesn't actually in practice do this. It seems like a really stupid way of reaching a solution. But actually sometimes it does. So if I want to find this invariant, I picked this example because, so you've seen invariant specifications already. I picked this, and in this case we've got the guard, which was the complaint I had before, that I didn't have the loop guard in it. CGIS genuinely, so the solution to this is x must be greater than 4 and x must be less than 1003. So if we do this with CGIS genuinely does this. Like, we keep going. Like every time, so it picks a candidate that works for some of the inputs, we get a counterexample, and then it's like, oh, I can just change the candidate like this. And it genuinely keeps enumerating like this and never finds it finds a solution eventually because that's a finite amount of enumeration. But it is a really stupid way of doing it. So one of the questions that you might ask in synthesis is, can we ask better questions? Like, do we have to be playing the game in such a stupid way? Yeah, you might want, another thing, can you give better answers? So if you're in the world where this is you with your great research idea, and this is your supervisor who's making stupid guesses about what your research idea is, perhaps you could start by giving some better answers to your supervisor. Yes, question?
How common is the enumeration problem in real-world program synthesis?
The example I gave you was a loop invariant benchmark. That's not uncommon. It's a problem when if you have a grammar that permits arbitrary constants, finding the right constant is really hard. So if you have a grammar that doesn't permit that many programs, then you're obviously not going to get that, but it's not uncommon. Constants are hard. So perhaps perhaps you can start by giving better answers. So this is sort of where oracle-guided inductive synthesis comes in. So what do I mean by an oracle? I mean anything that you can query and can give you a response in an oracle. So in the game, you are the oracle and your supervisor is making queries to you and you are giving responses. In CGIS, the verifier is the oracle. We can make one specific query, and that query is my program correct, this specific program here, and it will give, either it will say yes, or it will give you a counterexample. There's a very specific framework of query and response that it can give, And perhaps it would be good if we could go beyond that, so that in cases where we do end up in this enumeration, we don't have to play the stupid game, we can be a bit smarter about it. So this exists. There are many synthesis algorithms that use other oracles. So CGIS is the baseline. You will always find applications of CGIS. But there is a whole world of other oracles. So there's a nice paper by Jar and Sasha, which is called A Theory of Formal Synthesis via Inductive Learning, which sets out all of the oracles that you could possibly have and how these might work, and sort of the information you can get from them. And then we have a follow-on paper for that, which sets out an algorithm that basically says, if you give me an arbitrary oracle, this is how I do synthesis with it. But, yeah, so we didn't come up with the idea of oracles. There were people using them already. This is just a way of putting them in a framework. And if you were building your own synthesizer, you would intuitively end up building in some of your own oracles, whether you thought that's what you were doing or not. So in CGIS, your oracle is obviously something that just says, you say, is my program right? And it says, no, it's wrong on input 7. You can have oracles that try to answer questions about whether it's worth enumerating further down this template branch. Yeah, question?
So the word inductive, like used in what sense here?
So inductive synthesis is, so PDE is inductive synthesis, so you're going from a set of examples to a program. So if I've given you a set of input-output examples, you're trying, and you generate a program, that's called inductive synthesis. This is counterexample guided inductive synthesis because you're using the counterexample to guide the inductive synthesis bit.
Okay. Yeah, in the earlier case also, like the word inductive in the so why is the word inductive used there? Like generations. If I define, for example, natural number by N natural numbers by induction, I could define it that way, inductively define some data type. So does it have to do? I think it is used in a different sense here.
It is inductive in the sense that, why did they use inductive? It is inductive in the sense that you're trying to give a fixed number of examples and then you're trying to induce a program that works over this fixed number of examples. And I guess in proof by induction, you are usually trying to extrapolate a proof from a fixed number of examples. I don't know historically why they use inductive. PBE is called inductive synthesis. Okay. This is counterexample guided PBE, basically. Yeah, CGIS. Other oracles. So you might be able to have an oracle that can tell you whether a partial program is right or wrong and whether it's worth enumerating further down that. We have a paper called CGIS-T. There is also a paper by Ishal Dillig which uses partial evaluation. In this instance, what we do is we say, oh, I've got a template of a program. I've got most of a program. Is this correct? And what the oracle tries to say is the oracle then says, either it will say, yes, it's correct and I can complete it like this, or it will say no and don't bother with that template. Or it might say, I don't know, in which case you have to continue enumerating a bit further. But that can be quite useful if you can make that work, because you can rule out this enumeration where you go through different like the same program template with different constants. Invariance is a classic example where you can pick oracles. So there's more information than just a counterexample when you're trying to check an invariant, because an invariant can fail either because the invariant you gave doesn't hold in the initial conditions, or because the invariant doesn't imply the post condition, or because it's not inductive. And so there's a paper called ICE Learning, which will give you feedback on why your invariant failed. If you're in the world of, when we talked about what you could have as specifications, someone said data. If you're in the world of like like synthesizing functions where you've got a reference function, you might have a bunch of other information. So whilst you might be able to like execute your reference function as a black box, you can also extract other information from this. So you might be able to get like you might be able to get traces from it. You might get memory access, like the memory locations that are accessed. You could get the runtime complexity. Yeah, so there's work that goes beyond just doing counterexample guided inductive synthesis for that. Again, this is like, if you have an application, you probably have to design your own synthesis algorithm for it. And the way you do that is by using these oracles. This one is weird, but really clever. So, there's a thing called Oracle Guided Component-Based Program Synthesis, which is a really catchy title. The idea is that I am trying to deobfuscate some bit of code. I've got a grammar that I am synthesizing a program from, and what I want to know when I've got a candidate program is I want to know, is there another program in the grammar that behaves the same as the program I've just generated, but behaves differently on another program that is in the grammar? My synthesis is happening based on having a set of input-output examples, and then what I'm saying is, given I've got a program that works for my input-output examples, and I've collected those from the thing I'm deobfuscating, is there another program in the grammar that would also work for the input-output examples I've got, but behaves differently on at least one other input? Because if there is, then I know that my specification is not sufficient. So then I find that distinguishing input and I execute the black box on that input. It's quite a neat trick, but it does rely on you having this encoding, like being able to make this query that says, is there another program in the grammar that does the same thing except for that one input? Which means you have to have a constraint-based encoding for your grammar. But it's quite clever. I like that one. No one else seems to like that one as much. Okay, so I think I have an hour to talk about machine learning. Oh no, I should have made you spend more time implementing Segas. I genuinely don't think I'm going to take an hour talking about machine learning.
Maybe ask a question then.
Yes.
Given that you've got time. This is all about sort of program synthesis. I was wondering about sort of specification synthesis. Is there kind of work in that area?
Is there work in specification synthesis? By specification, so this is specification mining, right? This is the term they often use. So there is work on specification mining with program synthesis. So if you've collected data from your thing that you want a specification from, you could then use program synthesis to synthesize some kind of like predicates that are true for that data. And you could then use those as specifications. So I've been doing some work with one of my students, Leishi, on doing that for hardware. I ran a paper at FMCAD this year. The tricky thing is that if you only give positive examples, so a specification normally evaluates to true or false, right? And if you only give positive examples, then your synthesizer will just come up with the program true. So you need to give it some negative examples as well. You need to be able to say, these are behaviors that I want my specification to contain, and these are behaviors that I do not want my specification to contain. Does that make sense? Yeah. You also need a human to read the specification, right? Like you just move the problem one layer further away, right? Like instead of having a specification and generating the code from it, you generate the specification, but you still need a human to check that that's okay. What about machine learning? Why are we even doing this? Large language models exist. Surely we could just use machine learning for all of this. So there is a whole world of stuff that combines machine learning with program synthesis. And the reason for this is because the search space is intractably large, so it does make sense. The other reason is that programs are often underspecified. So machine learning, like heuristics learned from good programs, are more likely to guide you towards a reasonable candidate if you've got an underspecified specification. rather than enumerative synthesis, which will just give you the shortest, most stupid thing it's found. Well, the shortest thing, which is often the most stupid thing. So, there are a number of ways that you can combine ML and synthesis. So one of the most obvious things, which we are going to do in a little bit more detail, is so the grammars that we've had so far, they're just grammars, they're just bog standard context-free grammars with production rules. We might be able to place probabilities over those production rules and bias our search towards the more likely programs. So one of the easiest ways of combining ML with synthesis is to do this. We're going to talk about that in a little bit more detail. Actually, I don't remember how many of these. Actually, let's just do that now. We can come back to the others. Context-free grammar we had before. What I'm going to do is I'm going to put some probabilities over it. So I'm going to give you a function. So this P here. This is just a function which will assign a probability to each rule in my set of production rules. I've picked a context-free grammar because this is easier to explain with a context-free grammar. You might need context-sensitive grammars, and there is work that uses context-sensitive grammars. So where do you get your context-free grammar from? So you can get it from a number of places. So you might learn the weights for your grammar off a bunch of training data. One of the things that we've done is we've said, oh, what if we got a bunch of incorrect solutions from a large language model? Perhaps the solution, even if it's wrong, is in the right neighborhood of, perhaps if we're getting it wrong, they're in the right neighborhood of the solution. And so we can use this probabilistic context-free grammar to try and represent the neighborhood so that we're searching the right neighborhood rather than having to search the entire city. So to make this a bit more concrete, what you would do if you had, so in the yellow box is a grammar that's context-free. In the grey box is a bunch of solutions that you might have got from a large language model. The easiest way of getting this probabilistic grammar is you pass in the solutions and you count each time you used the production rule. You also want to probably give production rules that you didn't, everything a base weight of 1 so you don't rule things out. That was me counting them, I believe. You can then calculate the probabilities. So the way you want to calculate the probabilities is you want to make sure that for each non-terminal symbol, the sum of the probabilities over the production rules that you could apply is equal to 1. And so you don't want to find that you're in a production rule where the probabilities sum to more or less than 1. So in this instance, I've got 2 non-terminal symbols, I've got S and B, and so I've calculated the probabilities for the rules that leave S, so they sum to 1, and the rules that leave B, so they sum to 1. Yeah. So far, so clear? Okay, then how do I do the search? Well, the simplest thing to do is do top-down enumeration. So we've got this tree that we're searching. We start with a start symbol, and we said before that you had to learn some heuristics. What I'm going to do is, instead of picking my production rule based on like hard-coded heuristics, I'm just going to sample from the distribution over the possible production rules that I could apply, and then I'm going to pick that rule. And I'm going to keep doing that until eventually I end up either, again, I'm still going to encode a depth limit because there is probably a non-zero probability of an infinite program here. I don't like that idea. But yeah, I'm just going to sample top-down search. That is the most naive way of applying a PCFG to one of these search algorithms. Yeah, and if I hit the depth limit, I can either discard it or I can just force myself to complete it. It is worth noting that this is very much it's a bit of a bodge, right? Like the actual, so I collected solutions from a large language model. The PCFG that I produced is not an accurate representation of the probability of each the probability of getting a program from the PCFG is not the same as the probability of getting that program from the large language model. It's a very much a hack, because the large language model obviously isn't using a context-free grammar. Like, it has context. Yes, and then I return them to verify. And I do the same before. Okay. That was a really simple way of doing it. A slightly smarter way of doing this enumeration is to use A star. So, who is familiar with A star search? Some, about 50-50. Okay, so I'm still exploring this tree of partial programs. On this tree, I'm going to give every edge a weight. And what I want is so every edge corresponds to a production rule in this tree. So this edge that goes from E to C corresponds to the production rule that replaces E with C, and so on. But if I go further down, this edge that goes from 1 plus E to 1 plus E plus E corresponds to the production rule that replaces E with E plus E. I'm going to give every edge a weight. I'm going to define the weights. I'm going to define the weights like this, so that edges with a high probability have a low weight, and edges with a probability of 0 have an infinite weight. Okay, now I'm going to give each partial program a score. So, the score for each partial program is going to be a sum of the cost so far and an estimate of the remaining cost to get me to a complete program. So, for the cost so far, I am going to basically sum up the weights on the production rules that I've used to get there. So to get to this program, I would sum up the weights on the edges on the tree that I used to get there. So this is roughly the same as saying, this is the same as saying what's the probability of me producing that program. The weight is proportional to the probability of me producing that from my CFG. Okay, but now I need an estimate of the remaining cost to get to a complete program. That's obviously 0 if I'm already at a complete program, but if I'm not at a complete program, I need to estimate, if I'm here, like what would be the cost of me completing this somehow. So, what I am going to do is, I'm going to say that this cost. Okay, so it's obviously 0 if this is complete. So this means it's a string of terminal symbols. It is a complete program. If it is not complete, I am going to say that I'm going to calculate it with this h. So I'm going to say for every non-terminal in the program, I'm going to calculate the sum of the log of this h. I'm going to calculate that h by finding the fixed point here. I'm going to just do this with an example because it's easier. So initially, for what I need to do is I need to find this h score for every non-terminal symbol in my grammar. So I start off by saying that it's 0. Then I say, okay, I need to find the maximum of the probability of the production rule, every production rule that leaves that non-terminal symbol multiplied by the h score of every non-terminal symbol in the resulting rule. So I'm looking at all of the rules that lead me from E to something, and I'm looking at the probability of that rule and the product of the scores of the non-terminal symbols in the right-hand side of the rule. Okay, so for E, I've got one rule that goes E to E plus E, so the probability of that rule is 0.5, and the scores of HE is 0 and 0, and then the probability of the rule that leads to C is 0.5, and the score of C is 0 still, so that's still 0, the maximum of 0 and 0 is 0. But for C, I've got two rules again, but so C doesn't have an H score because it's a constant, so what I actually get is I get the maximum of 0.9, which is the probability of leading to 1, and 0.1 is the probability of leading to the constant 2, so I get 0.9. So at the end of iteration 1, I will have a score for HE and HC. What I will do is I will keep repeating this So on the next iteration, I'm doing the same calculation, but my scores for HE and HC have been updated. I will keep repeating this until I get a fixed point, which actually in this instance happens very quickly because I've got a very small grammar. When I have a fixed point, I then got an estimate of the cost of basically replacing each of these non-terminal symbols. Is that fine? Okay. So once I have a cost so far and an estimate of the cost to complete the program, I can start using an A-star search. So I'm going to have a queue that stores my partial programs with scores, and I'm going to initialize that queue with a start symbol. At every iteration, I'm going to pop off a partial program from the queue that has the best score, and I'm going to expand it. I only had one program, so I popped off the one program, and I've expanded it into 2 partial programs. I'm going to put those in the queue, and they've each got a score, and I'm going to pick the one with the best score, and I'm going to pop that off and expand it, and I'm going to keep doing that until I find a complete program. So at this point, you would assume that my constants will have the best score, and they do. So I keep doing that until I've got a complete program. I keep this queue going, and so at each point, I should be popping off the program with the best score. Yeah. This was a relatively simple way of doing it because I had a context-free grammar. So it is also possible to guide your searchers with context-sensitive grammars. So there's a paper called Accelerating Search-Based Program Synthesis using learned probabilistic models, and they learn a probabilistic higher-order grammar from a bunch of code, and then they use that probabilistic higher-order grammar with an A-star search. So your higher-order grammar means that each production rule has some context to it. I haven't got the slides to explain that because it's hard, and I didn't fancy it. It is also possible to guide bottom-up search. So there's a paper that uses PCFGs from LLMs to guide bottom-up search, which I mean, obviously they claim it's more effective than top-down search, and we claim that top-down and A-star search are more effective. So who knows? It probably depends on your application. Yeah. I also briefly want to tell you a bit about other machine learning other ways of combining machine learning with synthesis. So essentially the idea is that you want to learn some heuristics. One of the best way of doing this is to simply use reinforcement learning. So we're searching this top-down tree again. So in this instance, if you're applying reinforcement learning, the actions that your agent are taking is picking the next production rule to grow the program. And the reward that you are getting is going to be presumably a positive reward for a complete and correct program and a negative reward for a complete and incorrect program. The work that I have seen the work I've seen uses that as rewards. We have tried this for syntax-guided synthesis, and those were the rewards we used. I can believe that there are better rewards that would give you more guidance towards a good solution or a more readable solution, but thus far, this is all I've seen. You might also care about using neural networks to simply directly guess the programs. So there are many ways of doing this, but the obvious way of doing this at the moment is large language models. You can simply give them the specification and ask them to give you the most likely program. The challenge there is how you do any kind of guidance of the large language models. So there is some work that tries to use counterexamples to guide a large language model in your synthesis box, but there is there's a lot of prompt engineering there to try and get how you're going to get the large language model to actually obey the counterexamples you've had so far. You can also use neural networks trained to predict like the grammars that you use or the sketches that you use, and then combine those with enumerative synthesis to complete them. Yeah. So I'm going to say the new research, if you look at any new paper in program synthesis, it's going to be doing, I'm going to claim, one of two things, or possibly both of them at once. It's either going to be proposing a better guesser, so you're either going to have a different query response framework, so you've got some new way of giving guidance to your search, or you're going to have some kind of, this should have another bullet point, this should have some kind of better search algorithm. So like you've either got the guessers that are doing your search efficiently, or you've got some kind of better feedback for guiding your search, or you've got a new application. But those are basically your three categories of synthesis. It's either you've changed your oracle, you've changed your search function, or you've changed your application. Yeah, and I was saying, what if you want to use synthesis? Yes.
Sorry, could you expand on, you've got a different application, I didn't understand that.
New synthesis papers, it's either going to be, I've got a new synthesis algorithm, or it's going to be, I applied an off-the-shelf synthesis algorithm and I did it to something new and cool. So there's a lot of work that is like, oh, we used program synthesis to, to generate sorting kernels, or like we did something fun with it. Yeah, if you want to use synthesis, I hope you want to use synthesis. I would probably say the first thing you should do is, if you have a problem that fits into Cygus, you should try CBC5. You should try just writing it as a Cygus specification. You should try CBC5 because it's really fast and it would save you building your own synthesizer. If that doesn't work, or if you have a problem where you know some great heuristics and you know what the oracle should be, you're going to have to build your own synthesizer. That probably is the easiest thing to do, and most people will have to build a bottom-up enumerative synthesizer first because that's the obvious thing to try. And if you have a problem where you know partial solutions, you should probably try Sketch, which is the Solar Lazama tool. I don't think I had very much more to say. I think I should have given you more time to implement things. But yeah, are there any questions? Yeah.
So I was just wondering, where would types fit into this picture? Either as something to help with guiding synthesis, or something that makes producing well-formed programs harder than just context-free grammars?
Yeah, so one of the things that you would do when you're doing with the search methods, one of the ways to refine this search space is to have type-directed synthesis. So then when you're picking which programs you're building only the ones that are type valid. This is one way of pruning the search space significantly. Yeah, and there is a world of type-directed synthesis. Does that kind of answer that question? Yeah. I didn't give you types, I just gave you a very simple CFG because it's easier to work with. But obviously one of the things you want to avoid is you want to avoid enumerating programs that violate your type checking. Yeah.
A question about loops. I mean, all your programs have been created so far, right? All the examples have been created.
All of my programs are loop-free. If you want to synthesize programs with loops, the challenge is how do you check your programs with loops? Yeah. So you need to have a guesser and a checker. Your options are, so you can build a checker that is incomplete. So we've done some work where we're synthesizing programs that manipulate matrices, and so that obviously does involve loops, but we use a bounded model checker. So we say that we give you a bounded guarantee, we can't give you a complete guarantee. There is work there's work by Alvin Chung on verified lifting, where what they do is they will synthesize the program and the loop invariant simultaneously, and then you can check. So then it's only valid if the verification passes with the loop invariant and the program.
Well, I guess you need a variant as well, maybe. Can you generate variants as well?
Like a ranking function?
Yeah.
They don't. In theory, you could.
Yeah.
If your requirement is that your program terminates, then yes, I guess you're going to have to generate the program and the invariant and the variant. That seems quite hard. Yeah, that seems quite hard. I don't know of anyone that is specifically doing that. Yeah, loops are hard.
Yeah.
Why do we need loops?
And I guess in the same vein, recursion as well, kind of fits in the same bucket, right?
Recursion fits in the same bucket. There is a bunch of work on recursion, on synthesizing recursive programs. One of the so recursive programs are often synthesized using programming by example, but one of the challenges there is that you need to have. It's a lot easier if you have a complete trace of examples. Like if you have every time the program is called recursively, you need to have the example on which it is called. So if I've got like a program that, it's not enough to give me the outer input-output example, you need to give me the examples that happen inside the trace as well in order to make that work reliably. Yeah. Yes?
I imagine ranking function invariant synthesis is much easier than program synthesis, so programs with loops should be almost as difficult to synthesize as normal programs without loops, right? Because ranking function and invariant synthesis is an easier problem than program synthesis, I presume?
I think ranking function and invariant synthesis are a specific sub-problem of program synthesis. But when you're if you want to synthesize a program with loops, you need to, your options are either you synthesize the program, then you see if you can synthesize an invariant for it separately. So then you've got two stages, and potentially you can't. So that you can't synthesize an invariant, so then you have to go back and try a new program. Or you try and synthesize both of them at once in the same formula.
Like the invariant and the ranking function is likely to have like similar equations as the program. So by generating the program, you're sort of doing half of the work to generate the ranking function and invariance. It should be less difficult than like just a addition of complexity.
I think is the claim that synthesizing a program with loops is no harder than synthesizing a program with loops?
Not significantly difficult, more difficult.
What does not significantly more difficult mean for an undecidable problem? They are both undecidable.
I mean, in practical scenarios, run times will not be 10 times higher. That's one.
Potentially, yes. That there might not be a massive difference because often your invariant looks quite a bit like things that are in your program. But that relies on you having good heuristics for your synthesis. But yeah, they are both hard. I have not occupied all of your time. If you would, we could either stop early or I can meander if you want to continue actually trying to make the synthesizer work.
It's up to you. You want to vote?
We don't all have to do the same thing, right? Yes? Hello? More questions or votes?
More questions. For ranking function synthesis, I tried using Gurobi and it seemed to have less enumeration issues as compared to SMT solvers. Have you ever tried Gurobi for program synthesis?
Is Gurobi statistical? Is this like Daikon but for ranking functions?
I think what Gurobi is behind a license, so we do not know what it does. I just know it's MILC. Or maybe I just did not read enough about it.
I haven't tried it. Yeah, I haven't tried it. Sorry. Yeah.
I suppose it's more of a mindset question. I was thinking of a question to do with could you potentially do things to sort of rule out things when you're deciding what kinds of programs to generate? But I suppose is that just equivalent to putting that information in the checker anyway? So I was thinking, could you maybe apply some properties of the program semantics to be able to rule out certain generations of programs at the point that you're generating them? But I suppose that's just the same thing as saying no at the checker stage, is it not?
So you can, I guess type-directed synthesis does rule out things at the generation stage. You can also put a bunch of rules into your enumerator, so you can rule out stuff. You can rule out stuff based on syntactic rules in your enumerator. You can have your enumerator call an oracle that tells it to stop. This is the partial evaluation. You can have your enumerator call an oracle that says stop enumerating this path. That doesn't have to be the same oracle that does the ultimate check of your program. Yeah, there's no limit to the number of oracles that your enumerator can call. So if you have ways of ruling out things early, that's usually better. Yeah. Okay.
Can I ask one question?
Yes.
So this has been used for patching. I have a program, I know it's working with this input output. Give me another program that's almost it's identical in every other input to this one.
Has synthesis been used for patching? I can't give you a citation, but I'm going to claim yes. But I'm going to say this is one of the ways, if you can identify the bit that is wrong, then this is much easier because you can then say, now I'm in the world of sketching and I just want you to replace this hole. If you can't identify the bit that's wrong, then it gets a lot harder because you have to decide heuristically somehow which bits you want to try replacing. So you're then sort of searching a space of mutation rules rather than generating programs afresh. One of the bits of work we've done trying to do program lifting is instead of using a PCFG to represent the space of large language model solutions, we've just said get a solution from a transformer model and then try to repair that solution, and then instead of building a program bottom up, we're searching a space of rewrite rules guided by some heuristic about how wrong it is. Yeah, but I can't name you a paper that does patching of any particular real-world benchmark. I'm sure it exists. Yeah.
I was just wondering on practical side, I think you mentioned you had some project about converting C code to Rust code.
Yes.
Is there a way of encoding our desire to avoid undefined behavior or kind of, memory management problems, as it were, in the programs that we generate? So not just a kind of functional spec, but also a kind of spec that nothing goes wrong in this regard.
If you can encode it into an oracle, then you can put it in your synthesis algorithm. The question is, what does your synthesis algorithm do with the answer from that oracle? Because if the only answer is this is bad, then if you've got a synthesis search method that is based around some kind of machine learning that can receive a reward that says this is bad and then try to avoid it, then that's great. If you don't have that, then most likely the thing you can do is just say, don't return that program. But I don't know whether you can do anything smart with it if the only thing that your oracle can say is, didn't work, don't do that, please. Yeah.
Any other questions for Lisa? Okay, so lunch is here. You're more than welcome to stay in the room and hack and ask Elizabeth questions, but we need to make sure we give her enough time to have some lunch as well. She's been speaking. So I'd say just catch her in the break, or have lunch, catch her in the break, around. Otherwise, enjoy lunch. We do want to take another group photo at the request of Teresa and make an operator all parameters of the photos that we took yesterday. So